This is the tutorial for boundary layer number 2. Fluid having a density of 1.24 kg per meter cube and kinematic viscosity of 1.5 times 10 by the power of minus 5 meter square per second, flowing with velocity of 4 meter per second over a plate of 0.5 meter long and 0.6 meter wide. The velocity profile of the flow is in the form of u equal a plus by plus cy squared. Determine the velocity profile, the boundary layer thickness at the trailing edge of the plate, the shear stress at the middle of the plate, and the drag force on one side of the plate. So this is the question for this tutorial. So this is the answer. So from the question, they ask you to determine the velocity profile. It gives you the simple general equation for the velocity profile. What you need to do is you need to use the boundary conditions, create 2 or 3 equations, do the simultaneous solution, and then finally I hope you could derive that velocity profile and get this final answer. So it's the velocity profile that you need to use in this tutorial is u over u equal to y over delta minus y over delta square. And then by using that velocity profile, we substitute in von-Karman equation. We solve the boundary layer thickness by using the von-Karman equation, and finally you could get, and then we equalize the shear stress from von-Karman equation. This is the von-Karman equation, and shear stress from the Newton's law of viscosity. We get this term. We solve this problem. We do the integral to get the value of delta, and finally we get delta is 5.48x over Reynolds number. So you could refer this solution in our previous lesson. And finally, we substitute the value in this equation, and we could say that the delta is equal to 7.5 times 10 by the power of minus 3 meters. So I want to make sure here you need to understand which one is the width and which one is the length. So if the free stream velocity flow from left to right like this, so 0.5 meter will become its length, and you need to imagine that the boundary layer will occur from this edge and create and develop like this. So 0.5 meter is become its length, so we substitute the value of 0.5 meter in x in the equation. So if the free stream velocity is flowing from bottom to the top like this, so means now 0.6 is become its length. So we need to use 0.6 in the equation if the free stream velocity is flowing in this direction. Please make this thing clearly. And then here we need to calculate the value of shear stress at the middle of the plate. So, and then as I said, the length is 0.5 meters. So middle of the plate means that the x is now 0.25 meters. So we know that the shear stress can be calculated by using von Karman equation and Newton's viscosity law of viscosity. So, but Newton law of viscosity, the equation is completed. So we use the equation from the Newton's law of viscosity. Tau is equal to mu u over delta, and this equation is vary from time to time because it's depend on the velocity profile. For our velocity profile now, the second order polynomial, so the value of tau from the Newton's law of viscosity is 2 mu u over delta. So we need to substitute the value of delta, and then we need to calculate the value of delta. But we cannot use the value of delta from our previous answer because they ask the shear stress at the middle of the plate. So mean the x now is 0.25. So we substitute the value of 0.25. So we get the boundary layer thickness of this one, and we substitute in this equation. We could say that shear stress at the middle of the plate is 0.0280 Pascal. So this is the drag force on one side of the plate. So we, from our previous lesson, we could calculate from velocity profile, U over U. We use the von Karman equation, and finally we could come out the terms of the equation for drag force. So we do that one, and you could have this equation, and then we substitute all the parameters. So the mu is equal to rho nu. So please be careful about this, because sometimes question will give only the value of kinematic viscosity. So you need to understand that dynamic viscosity is equal to rho nu, which is nu is the kinematic viscosity. So you could replace it in this equation if necessary. And we substitute all the value here, so we get the drag force is 0.011899 Newton. Please bear in mind that we hope you could give a precise answer for in this chapter.